Yeah. Are you all back?
Yes.
Good. I have a cup of coffee, I hope. The next part here is control channels. I mean, before break, we talked about timing advance, power control, scheduling, and hybrid IQ. So let's jump to control channels. And the purpose of all these control channels, of course, you can have control channels on different levels and then different types depending what they're in. But the control channels here, I basically mean the layer 1, layer 2 control channels. The control channels carrying the scheduling decisions and then these type of things. And then, of course, you have control channels higher up in the protocol stack as well, but we do not focus on those here. So we basically have, if we start with the downlink layer 1, layer 2 control signaling, and the reason why I write layer 1, layer 2 control signaling is that the information originates in layer 1 or layer 2. So we have what you call the downlink control information, or the DCI in the downlink. It's transmitted on a channel called PDCCH, physical downlink control channel. And basically what it's transmitted there is typically scheduling grants, scheduling assignments. It could also be some other purpose like power control and so on. And the DU here monitors by running blind detection. It checks, is there any control message for me? If so, it follows whatever that message says. If not, it continues to monitor for control messages. In LT, we have some other control channels as well that personally I never liked, especially not the PC fitch, but we clean it up a bit in NRs. Now it's simpler. And the main, or maybe two main differences. Now we probably haven't studied the details of LT, but since NR is a beamformed system, we of course ensure that the control channels can be beamformed as well. That was not really the case for LT in the beginning. And we also made the structure more flexible so that we don't span the full carrier bandwidth all the time, which we did in LT. The reason why we did this change was, again, this ultra lean design principle. We don't want to block resources in a fixed manner, but rather have it configurable so that we can make room for future features. There's one downlink channel type carrying this. Then, of course, there could be multiple PDCCH channels running at the same time in a system. So one shouldn't understand it that it's just one channel, but one channel type, or that you have. So one such control channel, it's fairly straightforward processing, a little bit similar to LTE. We have the payload, whatever that could be, and that payload, depending on what type of messages is and the bandwidth and so on, it varies, but maybe 7 to 80 bits, something like that, could be a typical size. We attach a CRC, we do some, we implicitly encode the identity of the device, which UI are we addressing. Each UI has an identity. Then we do coding and rate matching, scrambling, QPSK modulation, etc. And we transmit it with its own DMRs, similar to what you do with data. So if you beamform this channel, you beamform the DMRs as well, and everything is fine. And there are some peculiarities when it comes to the polar coding here, how we spread out bits and stuff, but I won't go into that detail. It's very polar-centric details. Because for control channels like the PDCs, we use polar coding. If you remember what we talked about before the break, the choice of coding scheme was a bit controversial in NR and highly political. And then the compromise we ended up with was LDPC for data and polar for control channels. But on a high level, fairly standard coding chain, I would say. But then comes, there's a lot of abbreviations here, so bear with me. We have something we call the core set or control resource set. That's a time frequency region that you configure where the UI monitors for control channel transmission or PDC transmissions. So such a core set is 1, 2, or 3 OCM symbols long in duration, and it has a certain span in the frequency domain as well. So that is one such core set that we specify and we configure. And we can configure multiple of these core sets in a UE. We get to some figures later on where we can see that. And before we have configured anything in a UE, when we power it up and access the system first time, then of course we need to get some configuration very early on in that process, and that we get from the master information block, we get the core set 0, which is the first core set configured. And then we have something we call channel control elements. That's basically just a smaller piece of building block of building up this core set resource. And then we do blind decoding. So in such a core set that you is configured with, there could be one or more control channels transmitted intended for that device. Could be 0 control channels as well, but the device tries to decode whatever control channels it is assigned to that device on different search spaces. And if it finds a successful decode data, then fine, it follows that. And each control channel can be mapped to one or more control channel elements. So it gives a varying amount of time frequency resources here for coding a message. And the reason for that is to handle some form of link agitation. If you have a large cell with a user far out, you probably need some higher aggregation level, lower code rate. Whereas if you're close to the base station, you can probably do with less. So that is up to the base station to determine which code rate to use for this PDC sake, and the UE blindly decodes with not necessarily all of these, but the levels it has been configured with.
So Stefan, is that so then that with this set, that there is a set of resources where the UE knows that now there may be transmission, control transmission from me, and a set of aggregation levels, meaning that the set of coding rates in some sense that the UE expects, and these are pre-agreed, and after that the UE tests all combinations.
Exactly. So it's running a number of blind decodes. And I mean, if you remember this figure here, we have a CRC, and that is of course used to see whether this control channel information was correctly received or not, because if it's incorrect, then I don't care about it. But in that, in this control message, I also, not explicitly, but by flipping bits, some of the bits in the CRC, doing an XOR between part of the CRC and the RNTI, I implicitly encode the identity of the UE. So if it is for me and correctly received, then of course the CRC checks, everything is fine. If it is some noise on channel, so the CRC fails, or if this RNTI is for someone else, then the CRC check will fail and I don't have to bother. And to me, as one UE, it doesn't matter whether the message is intended for someone else or whether it's incorrect. In both cases, I should just ignore it. So that's why how you can encode this identity implicit in the CRC instead of having a separate bit feed for it.
And Stefan, another question: what would be the typical practice? I mean, would one schedule one? I mean, would one reserve one core set for several UEs, or would you rather have one core set per UE?
No, again, this core set is configured in the UE. I mean, one UE doesn't know about what other UEs do, but I mean, typically you would probably configure all UEs in the system, or many of them, with overlapping core sets. So each of the UEs have the same core set it monitors. And then in this core set, if you see it from a network perspective, I transmit control channels to whatever UEs I want to address. And all the UEs search for messages intended for them here, and some of them will find something and some won't.
And is this very dynamic? I mean, and does the core set allocation, time frequency allocation change? I don't know,
No,
100 milliseconds or so?
No, the location time frequency of this core set, that's a semi-static configuration. So that you configure and you leave it like that. And you can, of course, reconfigure it, but it's nothing you do very often, or if at all. So it's fairly static, I would say.
Okay, thanks.
And then, as I said, you can have multiple core sets in one UE. So this would be one example with the UE having 4 core sets configured. And maybe I have some of them in the beginning to handle the kind of slot. Let's say I do kind of slot-based transmission for most of my MBB data, then it's enough to schedule once per slot. So I have a core set for control information there. I check at the beginning of each slot if there is some data for me, if so, and then I get data. But then maybe I have some ultra low latency, very urgent serves as well. So I need to check my control channels a little bit more frequently. I have some core set 4 here in the middle of a slot as well, where I can check for control signaling to see if something very urgent is coming in. But as I said, these core sets, they are configured so they can have a resolution in the frequency domain of chunks of 6 resource blocks and 1, 2, 3 of them symbols in time. And I can also reuse the core sets for data. So let's say I configure 2 core sets in this UE, so it looks for control signaling in both of these. And it found something in this one, some downlink data transmission, so it starts to receive the blue data. But the control channel you find there could actually point to that the data transmission starts already in the first OFM symbol at the same time as the core set. And to do that, I use this reserved resource mechanism. I don't think we went through that. That was probably one of the hidden slides. But there is a possibility in the downlink for the data channel to declare some time frequency resources as reserved, meaning that I should not expect data to be mapped on those resources. And I can configure a number of these patterns, and then I can dynamically indicate whether any of these reserved patterns are active or not. So basically what I do here is I actually implicitly get a pattern configure reserved pattern such that I can indicate that with a bit in my downlink assignment that yes, the core set where you found your data channel, that is a reserved resource. Don't expect any data in this gray box. But in this one, that you didn't find a valid control channel in, there you should expect data to be mapped. So that's the way you can reduce the core sets that are configured but not currently used in this particular time slot. You can use them for data. Maybe that sounded more complicated than what it is, but the idea is to avoid always ending up in this situation where I need to waste 2 OFM symbols, even if I just use this part for control signaling, to be able to reuse this unused area around it for data as well.
And then is there, because you kind of indicated that the concept of slot is becoming kind of a pseudo concept. And in some sense, you create everything on the fly now here using this control signal. So does it mean then that there is no a priori assumed length of the scheduling, let's say resource duration, that you also schedule that dynamically in this channel now?
Yeah. Yes, that's correct. I can schedule 1 OFM symbol of data if I want to, or 5 symbols, or up to 14 symbols. So that's dynamics. I could, in principle, if I want to, just schedule parts of this, let the data transmission stop here, and use the rest of the symbols here for something else. That's perfectly fine. That gives you a lot of flexibility. Maybe you could decide that let's use those symbols for data transmission to some other user, or maybe you can use them for uplink data transmissions, or maybe you want to use them as guard in a TDD system or something else. So that's part of the scheduling assignment, the length of the downlink data transmission. And the same way in the uplink, part of the scheduling grant is how long it is, how many symbols you use. So this type of slot notation is basically just used as one kind of convenient way of denoting certain time instances. but that doesn't really mean much. So if one could rewrite the specifications, I would probably remove the word slot completely and make it even more clear in the spec. But for historical reasons and things like that, it remains there.
Thank you.
And as we talked about, we do blind decoding of the control channel or control channels using these search spaces and Dci formats. And you can have different, as I said, aggregation levels, basically different code rates this will correspond to. And I have a very flexible configuration. I could set up core sets like this. I have the blue one that I monitor at the beginning of each slot, green one that I monitor more often, and then a red one as well that I monitor just every second slot. For some reason, I monitor here, but not there and there. So all this could be one configuration for one UI. And then that UI would do blind decodes in all these green, blue, and red areas and see if it finds something intended for that UI. And I could have a different configuration for another UI. And these search spaces, that basically tells you where within this core set can a control channel be located. Because we have said, we have put some structure in it. If you have an aggregation level of one of these control channel elements, then they can start anywhere. But if you have an aggregation level 8, then they can just start on every 8th position. So there's a little bit of structure in when we have specified them. Then we have also randomized them over time in a UI-specific manner. And that is exactly to handle this case if you put configure two UIs with core sets overlapping in time and frequency, which is a typical case. Let's say I wanted to schedule this device A on this highest aggregation level 8. I use those control channel elements for that. Then those time frequency resources are busy because I use them for device 8. I can't schedule device B here on the same resources. So there's an idea of randomizing this over time. So at this point in time, they actually collided partially. But at next point in time, next time slot, maybe the red one is monitoring over here and the blue one is monitoring over here, or the blue one is here and the red is there, or something like that. So it varies according to a pseudo-random sequence, taking the UI identity into account. So the idea here is that two UIs should not be constantly blocking each other. So if two UIs are being blocked right now by using the same time frequency resources, I can't schedule both of them at this point in time. Maybe I can do it at a later time instant. If I would be fine with aggregation level 4, then I can schedule these two devices at the same time because this one is over here and that one is over here, and they don't collide.
But let's say that is the length of these now that you have this long is the possibility to schedule 8? Or?
Yeah, this would be aggregation level 8. So here I would check with a certain low code rate that requires 8 resources in the time frame.
But if you have, is this now 8 units of resource that you have there, or is there more than 8 in this?
In total, this device, it tries to decode one PDC set using these 8 resources, and then it tries to decode another one using these 8 resources.
But then the collision is not only partial now, isn't that so then? That in the first, if you could use the red one, the first 8, and then the
blue one can use those. Yes, that will be fine. So they don't collide. So I could, if I can use this one, then they wouldn't collide. If I have to use that one, then they would collide. So in this simple toy example, I would probably be able to schedule both at aggregation level 8 without colliding.
Okay.
That's true. I should probably be a little bit clearer on that.
But the red one still has, in this case, it has 2 different alternatives for this 8, and
yes.
not like
exactly. In this example, it checks for 6 candidates with aggregation level 1, 6 candidates with aggregation level 2, 2 candidates with aggregation level 4, 2 candidates with aggregation level 8, and none with aggregation level 16. Okay. That's what this particular UI has been configured with. So it does all these blind decodes and see if is there anything for me there. So it can be scheduled using this one, or maybe that one, or that one. That is unknown to the UI. So the network has the freedom to, if it thinks that the UI is in a challenging situation, link budget-wise, it can use this one. If the UI is close and not so challenged, we can use a short one.
But doesn't this lead to some new, let's say, novel coding theoretical problem how to design this?
What do you mean we design this?
If this is kind, you have a UI, you have the red, you have the blue. There is a certain sequence of these that you want to allocate. So then, how many UIs can you put there with a given control, let's say collision probability or mask probability and this kind of thing?
Yeah, in essence, what you get there is some form of scheduling problem. You have a bunch of devices in your system, you want to schedule them, and you look at how good the data channels are and what data they have and so on. And then you need to figure out, can I schedule all these devices at the same time, or will some of them have colliding control channels so that I can't schedule all of them? So the scheduler also needs to check that actually, and that is a relatively large part of the scheduling complexity. It's not trivial.
Mm-hmm.
So from a network perspective, of course, I would like all UIs to check all aggregation levels at all positions all the time. Then I have the full freedom on the network side. But then on the other hand, the UI would be very complex and have to look at many different places and do a lot of processing. So from a UI perspective, the UI vendor probably just would like to try one of these hypotheses. That would be best from a UI perspective. And then you need to find a compromise between the two that gives you reasonable UI complexity and at the same time good scheduling flexibility. And I think we get to that to the next slide, because that was actually quite a large part of the control channel discussions in 3PP. But before we do that, I should probably mention also the common search spaces. These ones were UI-specific, randomized over time, but there are also messages that are intended for multiple UIs. For example, scheduling of system information that tells all the UIs about the configuration of this cell. Random access response, or paging messages and things like that. They need to go in the same way for all UIs. And then, of course, it's very easy. You just specify, we always use this part of it for common search space. It's not randomized over time. So some of the candidates are kind of fixed in time as well. And then comes, to make it even messier for you, the Dci formats. And that basically tells you the purpose of the DCI, and also a little bit on the size. So we have format 000, that's uplink scheduling with some limited possibility and not all bells and whistles. And 01, that's uplink scheduling where you can configure all kind of things you need. And same thing for downlink. And if you look here, it's an example of the downlink. Here's all the type of information that you may want to or may need to convey to the device in order to schedule it in the downlink. So this is the carrier format indicator. If you do carrier aggregation, you need to tell the UI which carriers or if it's scheduled upon. Which bandwidth part is it scheduled upon if you want to switch it. Where in the frequency domain is it scheduled? Where in the time domain? There's some mapping things you need to put out there. Modulation scheme. Is it a new data transmission? So I should clear my soft buffer, or is it the retransmissions that combine it with what I have in the soft buffer? If so, with what redundancy version? Same thing for second transport block, some hybrid IQ related information. Which hybrid IQ process is it? Like that, multi-antenna related information. and also where should I transmit my push feedback axon. So there's a lot of information that you need to give to the UE, and some of this information is not necessary unless you use that feature. For example, many of the multi-antenna feeds, if you don't do any MIMO and you just do single antenna transmission, you don't need all this stuff. So then you don't transmit it. Then you have configured your Dci format in such a way that these fields are ignored or not present. And if you use a lot of MIMO, then you're configured with the appropriate fields here, so that because you need to convey that information. Same thing with carrier aggregation, for example. If you don't do carrier aggregation in your system, there's no point in wasting bits on that, so then they're not present, and so on. So that means that many of these bit fields, whether they're present or not, and how many bits you use for them, that depends on the configuration. And in order to get that configuration, you need to be scheduled with the downlink transmission. So there is a need for a Dci format that is kind of independent of your configuration. And that is this fallback format. It has reduced flexibility, not all bells and whistles, but it's more of a fixed size. So that you can use it for data scheduling, but at least you use it for receiving the configuration at the initial setup on how the more advanced format is configured, what fields are present, and what multi-antenna schemes have I turned on in this network, and so on. So that's why we have two fields, both for uplink and downlink. Then we have some features here where I think it's not that useful. You can skip those. We have some power control related formats that you can use to send bits for power control purposes. And then in release 16, we have more features in the system, so some additional Dci formats popped up. But basically, the Dci is all these information fields that I need to receive downlink or transmit an uplink. And depending what feature I've turned on and what bandwidth I have in the system and so on, the number of bits in the Dci varies. But maybe you can think of this one as like 70 to 80 bits or so. Something in that ballpark. Could be less, could be more. And then we said the device is doing blind decoding. It's told to blindly decode a number of these formats. If you look at the downlink scheduling, for example, this one has, I said, this has less number of bits, this has more number of bits. So here you need to try two different hypotheses. You have to try all the different locations in all the core sets you're configured with. And you have to try all the different aggregation levels you're configured with. All that combinations you have to try and blindly see, is there something for me in one or more of these combinations? And that can get quite complicated. I mean, if you give the full freedom to do whatever you want, you will end up with a huge number of blind decodings in the UE. And if you say that the UE is just blindly decoding one format, then of course you lose all the flexibility in your network. You can't use different Dci formats, you can't use different core sets and so on. So we agreed on the number of blind decodings the device is supposed to be able to handle. 44 in case of 15 kilohertz sub-carrier spacing, and then a little bit less for the other ones. Then you also need to look at the number of channel estimates for the PDC stage, because decoding is not just decoding, it's also estimating the channels. So there's a limit on that as well. And then there is also a limit on the number of DCI sizes that the device can handle. We have the 3+1 rule, which basically means that the UE is able to check 3 different DCI sizes very rapidly with time-critical scheduling information, and one size which is less time-critical to use for power control or some not as time-critical things. So there's a number of these limitations that the UE needs to do at least this much. And all that together gives you what PDC said candidates you can look at. So it gets quite, although the principles is not that difficult, but when you go down in all the details and write specification, it gets quite difficult, especially these sizes here. Because if you configure a number of different DCI formats you want to check for, you can't check all these different sizes. Then it happens that 0, 0, and 1, 0, they are always the same size. You do a little bit of padding on those. 0, 1 and 1, 1 could be of different sizes. So already here we have consumed 3 of these time critical sizes. And maybe the +1 size for power control. Then you can't do this. So if you want to do that as well, maybe you need to size align some of the messages with a little bit of padding, etc. So there's a long text in specification describing how to do this size alignment and get everything within the boundaries what the user is able to do. So that gets a little bit less fun to read, but that's the idea behind it. Then from a network perspective, we would like the UET to do everything. From a UI perspective, I just want to do one thing, one decode, and the compromise is something in between.
And then you say that now it is so that there are 3 specific sizes per UE that are agreed, and those. But these 32, no, 20 to 44 alternatives, so they include these 3 different combinations or are multiplied with 3.
No, they include the different. I can configure up to 4 different DCI sizes. And I look for all 4 of them, but I'm not allowed to violate these other 2 blind decodes and channel estimates and so on. So you need, when you pick a configuration for a control channel, you need to check that you don't violate this, because if you do, then you can't guarantee that the UI will be able to handle it. But that's doable. I mean, you can sit down with pen and paper and check that, and then you find a couple of good combinations that are suitable for your network purposes, and then you use those, and everything is fine.
So is it now so that this is the fundamental meaning of a 1 millisecond slot in 5G new radio, is that it is a time unit in which the number of blind trials of a UE is restricted to be some sensible number?
Yeah, something like that, you could say. So that's where the slots end up. You can do some of your time domain allocation referring to slots and so on, but that's basically what it means. And that's also why you see this number decreasing, because the slot length is getting shorter and shorter. And if you would keep 44 also for the very short slots, then it would be too burdensome for the UE, according to UE manufacturers. So that's why the number is a little bit smaller. On the other hand, you can do more monitoring per millisecond. So. Okay. They're definitely a bit messy. And then, but I think what you need to remember is just that you do blind decoding of the control channels, and that there are some limitations on how many you can do. Then I have a few slides on some of these fields. For example, frequency domain allocation and the time domain allocation. And I also think the TB size. You can look a little bit at those. So in the frequency domain, you can configure 2 different resource allocation types, and you set one or the other. And either you have a bitmap, where basically bitmap points to pairs or quadruplets or so of resource blocks that you're scheduling. So if there's a 1 in the bitmap, I'm scheduling on those 2. If it's a 0, I'm not scheduling on those 2. Or you can use the start and length, so that you start on resource block number 3 and you schedule 7 resource blocks or 8. And these 2 you can encode with a decent number of bits. So you configure one or the other, or that you can dynamically switch actually. And then also in the timing wise, if you find your control channel, you need to know where your data starts. And you could, in principle, of course, put all that information into the DCI, but that would be a little bit too much. So what we said instead is that let's configure a table with a number of rows in. And each row contains the slot offset. Basically, if it's 0, then it's the same slot. If it's 1, then it's the next slot. Start symbol within that slot, and the length in the time domain. And then also the PDSH mapping type has to do with some DMRs mapping. And the release 16, we can also have some other things here. And then the DCI just points into one entry of that table. So if you have value 2 in that time domain resource allocation field, then you know, it's what's written in this line that tells me where to find my data channel, my data. In this case, it was the next slot and 3 of them symbols into the slot. And you have the length as well. So then by configuring different tables, you can match different scheduling behaviors. So you typically choose a table content that is kind of nicely goes together with how you intend to schedule data transmissions in the downlink. And since you need to be able to be scheduled for some initial data transmission to get some system information and so on, there are default tables that when you power up your device and you have some default tables preloaded, so to say. And if you're fine with these values, they are chosen, so that should be decently okay for normal scheduling as well. Then you don't have to configure the tables, but you can, if you want to, you can reconfigure these entries to something else. But you have a default table. And the transport block sizes, you need to figure out how big is the payload, and that's basically a formula or procedure that calculates that based starting from the modulation coding scheme, the number of resource blocks, number of layers, and some other things. You can calculate what is the transport block size here out of that. So then you know the payload size as well, and you can know how to do rate matching or rate dematching, so to say, and what the code rate is for the error correcting code and all these kind of things. So that was it on the downlink, at least the stuff I intended to cover. Then we also have some uplink control signaling called UCI, uplink control information. And that you can transmit in 2 ways. Either you can transmit it on a separate uplink control channel called PUTCH, physical uplink control channel. And that is the typical case. If you don't have any data ongoing in uplink, then you transmit it on PUTCH. Or you can transmit it on the push. And that happens if you have an ongoing data transmission in the uplink, and at the same time you need to feed back some control signaling. You could, in principle, transmit push and PUTCH at the same time, but that would increase the peak-to-average ratio and lead to some other nasty RF interference scenarios, intermodulation products and things like that in some combinations. So that was not so desirable from a practical perspective. So what you typically do in that case is that you put your UCI on push. So it should be UCI on push here. It's a typo. And that uplink control information, that is hybrid AIQ acknowledgements. Remember, we talked about the retransmission protocol before the coffee break. So you know where it's ACK or NAC. It's the channel state information so that you can assist the downlink scheduling, it's the scheduling request and things like that. And that uplink control information is somewhere in the time frequency region. And it is indicated in the downlink control information where to transmit the PUTCH. So if I schedule the user or the device to receive some downlink data, as part of that downlink scheduling assignment, I also, if you remember this table over here, I also have some PUTCH resource indicator, which basically is an indicator telling you where in the time frequency domain on the uplink should I put my acknowledgement. So one can say that the UCI is scheduled as well in conjunction when you schedule the downlink data. And if you do carrier aggregation, typically you have a lot of carriers in the downlink, and maybe not just one in the uplink. That's the typical case. So then you have to put all the PUTCH information on one uplink carrier. We could also do it in 2, but I don't think this is used in practice because devices typically just implement one uplink carrier. We have 5 different PUTCH formats, or 4 maybe, because 3 and 4 are very similar. And they are, you can basically view them this way, that either they have a small payload up to 2 bits, which would be 2 ACK-NAC bits, for example. Or it could be more than 2 bits, could be in the worst case 100 bits or even more than that. And that would be for if you have a large number of ACNAC bits and a large amount of CSI information you need to send back. And then you can transmit that either across a small number of symbols, because you want to get it back quickly and you have a good link budget, or you can stretch it out over a large number of symbols. And that is if you you have more of a link budget constrained system. If you have, especially if you have a large number of bits, maybe you need to spend a number of them symbols on that number of bits to get a decent EBRN note for all those bits. All these push formats are designed with low PAPR in mind, and regardless of if you do DFT pre-coding or not on the data channel, all these push formats are good for both. I won't go through them. You have the examples in the slides. So many of them are basically you play around with sequences and do different phase rotations and things like that to get different constellation points when you want to send back. That happens to be push format 0, and you can do it over a longer time duration. Then you still have a lot of sequence stuff you play around with. Or if you have the larger payload format, then it's more kind of traditional CRC channel coding QPSK, and then you map it out over across whatever resources you have set up. And then a few words on timing. Yeah. And I think I've said this already, but when I transmit something in the downlink, I also need to tell the device when and where in uplink to transmit this acknowledgement. So that is part of the downlink control information. I basically point into table here as well, and that table tells me when in time. So here I will point into row 3 and get this delta 3. In this scheduling, I will probably point into row 2 to get kind of delta 2 and other time duration, or point to the same slot, and then you get all the ACNACs at that point in time. You can, of course, point it to something. I mean, this one was a relatively quick ACNAC, and maybe you can even point to the same slot in the worst case. Because the processing here, I think the DLT part of the table, you just see 2.3, but 2.3 milliseconds. That is the amount of time an LTE can spend on decoding data before sending an ACNAC. If you compare that with what you have in NR, you see it's much shorter in NR. It's fractions of a millisecond. Depends a little bit on how you have configured your demodulation reference signals. If you just have them at the beginning, it is quicker, but if you have spread them out, it takes a little bit more time, because then you want to spend more time on channel estimation. And you have UE can be 2 categories, either baseline UE or more aggressive UE with lower latency time. So you see, sometimes it can be very, very quick. 80 microseconds instead of 2.3 milliseconds. So data decoding can be quite fast in NR if you want to, which is good for this low latency aspect again.
So this is the time from the start of the transmission to the time when it is available at the UE.
I think it's the end of when the transmission ended until you have you can send your ACNAC. So it's basically from the end of this blue here until the ACNAC transmission instant.
Okay.
It can't be from the start, because I mean the duration of transmission can be longer than these numbers.
So in some sense, the protocol as, let's say, cost of round trip or something like that. How much it takes to how much okay, this is a time that somehow the protocol is adding to the round trip time, or what, in some sense.
Yeah, I mean, in the ideal case, the UE would be super fast in decoding, and when you have sent the last bit, it will already have decoded everything. But in practice, the UE needs some time to decode, so it takes some time before it can send that. It can, of course, send it much later if you want to. I mean, this first downlink slot had a DAC quite late because it was told so by the network for some reason.
The allowed processing time, let's say.
Yeah, this is the allowed one. The UE must be able of doing this. But then the network can configure it to be slower, of course.
But if you think on it from the UE implementation's perspective, it should say much shorter processing time requirement than in LTE, right?
Yeah, exactly. You should probably add a word requirement here as well. You don't have to. You can, of course, schedule this to be equally slow as an LTE if you want to. But the UE cannot count on that. The UE can't really exploit that in the implementation.
Mm-hmm. Okay.
I think there's just one more slide left, and I think I said this as well, that if you have a control and data at the same time, then you put the control information on the push channel, and there's a set of rules in the specification how to multiplex or puncture these UCI into the data channel in that case. And so both the UE and the network knows where to find this UCI in this case and can grasp it from the uplink transmission and decode it. That was it on the control channel stuff.
And is that now so that in the last part, when you talk about what was like cell search and this kind of, so that is also in some sense related to control information, but on a less dynamic level?
Yeah, you can say so. I mean, sure, that's also control information, but it's not this type of scheduling control information. It's, as we said, less dynamic. So that will come up as well. And then, of course, you have yet another class of control information. That's all the configuration that is sent with ROC signaling. That is sent across the normal data channel as seen from layer 1, but then in the upper protocols are used as control information. But that way we don't cover much here, but we'll see a little bit of other types of control information when we do cell search and random access.
So do we then take a 50 minutes break again?
Yeah, that's my suggestion, unless you have something else you want to talk about on control channels.
Questions?
Maybe you need another coffee after this session.
It is complicated.
It is. And control channels is I mean, it's been a lot of time spent on that.
It's a bit dry.
Yeah, it's very basic. I mean, designing the data processing chain is relatively straightforward. Then you get a little bit on multi-antenna, things may get a little bit complicated. And then you come to the control channels where you basically restrict everything, because what you cannot signal on the control channels, you cannot do, even if the structure would allow that sometimes. So the control channel basically define the system to a large extent, what combinations that are supported and not, and so on. So it gets quite complicated.
Yeah.
But I hope
how does this physical layer of 5G NR incorporate machine type communication?
It is the same set of channels as we had here. And then, of course, depends what you mean with machine type communication. If I mean, low latency was quite a lot in focus in NR. So that type of machine type communication, if you want to schedule something for very quick response, etc., it's just what we have looked up on here. There are some enhancements coming in that area as well in release 16 and 17. If you with machine type communication mean this massive MTC type of very simple devices sitting out there reporting temperature, then you will probably do narrowband IoT or LTM for those. That's not really addressed by NR. But then instead, since NR can coexist with LTE technology, you put them on top of each other, and it will be an integrated part of the 5G system in that way.
So yeah, so that was my question. So it is not a part of NR. If the payload size, for example, is very small for those devices.
I mean, you can, of course, do it with NR, but it may not be the most efficient way to do it. If the only thing you want to do is to transmit a relatively small payload quite infrequently, you want to run on battery for a very, very long time, maybe you don't choose NR, maybe you choose narrowband IoT or LTM instead. So I would say that even though these two technologies appear in the 4.5G time frame, so to say, 4G time frame, they are also part of the 5G family and nicely integrates into the 5G technology.
Okay.
And then we have something called RedCap, or reduced capability, coming in release 17. And that is kind of a stripped down version of NR. You remove some of the more advanced MIMO modes and things like that. So you can build a very simple device. And that would sit somewhere between the narrowband IT, LTM type of devices and the high-end normal NR devices, and fill that gap in between. So that would be some kind of more advanced massive MTC type of thing. If you need a megabit or so in some industrial setup.
Does it have any specifications, this red cap?
It's coming in release 17, so those specifications are almost done.
Okay. Okay. Thank you.
Hmm?
Nice.
Final copy?